Hi, my name is Julianna Posey. I am a grad student at the University of Maryland, Baltimore County, and my presentation today is on the repeatability and performance prediction of additively manufactured 17-4 stainless steel. So, metal additive manufacturing. What's the interest? Why do we want to use metal additive manufacturing? Well, it's a very viable and versatile alternative to traditional manufacturing methods like forging or casting. It can be digitally designed, which is really helpful, especially for on-demand products. And metal AM components minimize waste and are cost-effective, particularly when used for intricate, weight-critical, or low-volume applications. The specific type of metal additive manufacturing that my work explores is powder bed fusion, which essentially involves two powder beds, one that's filled with fresh powder and one that starts off empty. As the process begins, a roller pushes fresh powder across a base plate. This is also done within a heated, argon-based chamber. So the build plate bed lowers, the powder delivery bed raises, and then the laser beam source hits a scanning mirror and fuses the first layer slice. This is continued, and this is sort of an image of what it kind of looks like. So layers are first outlined with a contour pass, and then they're filled in. And every time they're filled in, they're rotated by 90 degrees. So this is done continually until eventually your whole component is built within that powder bed. So the objectives of our repeatability study. Well, we have this selectively designed build plate. Now, the build plate itself is made from precipitation hardened 17% chromium, 4% nickel, which is known as 17-4 pH stainless steel, and it was built on the EOS M290 system in an argon environment. Now, why is the Navy interested in this? Well, they're very interested in parts that are highly resistant to corrosion, as well as have a high tensile strength. And the complex martensitic and austenitic microstructure is one that they want to explore, particularly coupled with that additive manufacturing component. So our main two aims here are to seek cross-locational consistency through processing parameters. So basically, we want to be able to print this build anywhere in the world on any sort of machine and get the same exact results every time. We don't get that right now, and that's why we're trying to figure out. The other thing that we need to do is develop a testing framework to determine the microstructure property relationships. And so that is a lot of my job, figuring out what needs to be tested exactly for us to understand what's going on in the build itself. So let's look at the build plate. So here you can see we're only looking at a certain region, and this region has what we call thin fin structures that are built at varying angles and thicknesses, and zigzag structures, which are built at varying width reductions. So here's some more information on the thin fin structures. They're built at a 45 degree, 55, 65, and 90 degree build angle, as well as 3 different thicknesses, 1 millimeter, 2 millimeter, and 3 millimeter. We want to see how that impacts a variety of properties. And now zigzag structures as well. So 4 of them are built with wide bases, and 4 of them are built with narrow bases. And they're also built with either 20%, 40%, 60%, or 80% width reduction multiple times throughout the build. And now this was done to influence a complex thermal history, which might provide insight into different microstructures that would appear. So what are we looking at? What are we trying to find out? What's different? How is the build plate change? So these are our methods of characterization. We're going to be looking at microstructure, surface roughness, some hardness indentations, then moving further up to microsample tensile testing, macrosample tensile testing, and then eventually we want to apply this into situations where you could use this on a ship. For the purpose of this presentation, however, we're mostly going to be focusing on the microstructure and the surface roughness. So here you can see the microstructure that we were able to get from one of our thin fin surfaces. And you can tell it's very distinctive melt pools that point in different directions, and that's, as I previously mentioned, the cross-hatching. You know, as each layer is fused in a different direction, it forms these crisscrossing patterns. And it's approximately 9 melt pools per 1 millimeter. Now, moving into surface roughness. So it's very important to understand that the difference between an upskin and a downskin surface. So here the thin fin structures and the zigzag structures were built to have both of these types of surfaces. What a downskin surface means is that it rests upon the powder particles as it is built. And as the laser is going down, that means that there's very little room between the fused layer and the particles underneath. The upskin surface doesn't have that as much. There are some particles that rest on top. Now, and you can see that it's both for thin fin and zigzag structures. This is what a structure surface sort of looks like. So we do have some partially fused particles, clusters of unmelted particles, but we can also see melt pools in there. And we can see how the laser has melted the metal and how it's flowed. Now here we're looking at the upskin surface. We were able to get these really great images, and essentially what has happened is as the angle decreases, we see more and more of these, image-wide layers and the elongation of the melt pools. We also see less instances of clusters of powder. And it's the opposite on the downskin surfaces. We have an increasing prevalence of powder particles and a decrease in the visualization of those flowing melt pools. We can actually see this in the data. We used 2 types of methods to measure the surface roughness. One was using a stylus and one was using a Keon's confocal microscope. The confocal microscope was really helpful for allowing us to visualize what we were looking at, but this data here is from our stylus measurements. And what we saw here is, again, the roughness increase is as the build angle decreases. Likewise, the downskin roughness was a lot greater than the upskin roughness in almost all cases, except for 90 degrees, which technically doesn't really have that upskin and downskin surface. We also realized that roughness is not necessarily impacted by the thickness of the structure build itself. This was further shown in the wide base and narrow base zigzag structure roughnesses. Now, the other interesting thing here is that height within the build doesn't really affect the roughness. We again see, steeper surfaces for the downskin have an increased roughness, but it doesn't really matter where the height is. It's still going to be around the same large value. So our conclusions: rougher surfaces are a lot steeper. We're going to look into our microsample data and our hardness testing next. So the microsample tensile testing, it'll yield us some multi-axial data within the build itself. And the macrosample testing can be observed and compared with the microsample testing for higher spatial resolution. Also looking into the microstructure more, seeing how the microstructure of the zigzags structures, how the thermal history has impacted that microstructure and thus the actual behavior of the material. All of these, the roughness, hardness, and those tensile values are going to be examined for different relationships. These are my acknowledgements and references and contact information. Thank you so much.